All right. Okay. So, welcome back, everyone. We are now excited to welcome Nick Chia, who's going to talk about AI agents for autonomous labs. I think this is a very exciting frontier where leveraging agents to sort of control automated experiments is a very important frontier that is pervasive now across biology, material science, and it's really, I think, representing the next sort of leap. And one of the cases where we are seeing very great success stories immediately, actually, in terms of being able to integrate agents mostly reliably. And I think Nick is going to talk about those kinds of issues in terms of integrating agents into these autonomous labs. So, with that, Nick, over to you.
All right, thank you very much. I'm Nicholas Chia. I borrowed this set of slides from Brian and Priyanka, but I'm one of these people anyway. And then, I'm going to talk to you about AI as autonomous agents running an autonomous lab, right? And so, the first thing to really think about is what do we mean? Let's define some terms, right? So, how is an autonomous lab different from, I don't know, other laboratory equipment? How is it different from, digital droplet PCR, right? Or different from any of the other automated machines in the laboratory and that carry out some kind of automated tasks, repetitive tasks over and over again. How is it different than a plate reader or a confocal microscope that scans, right? Well, it's different because like those systems, they can include some kind of automation, some kind of robotic automation. In this field, we often think about that as a robotic arm because in computer science, there's a lot of work using robotic arms for this kind of thing. But more than that, the automation is not the defining aspect of the system. The real defining aspect of the system is the fact that it's got a decision-making engine that is AI powered, right? And so having a decision-making engine means that it can become a closed loop system. So all the other systems kind of require humans to intervene to make decisions about how to use those devices. And the reason why autonomous labs are so exciting is because, by stepping back, by using the AI and allowing the human to step back, the human can think at a higher level, right? And doesn't have to, carry their plate around or do this kind of thing. So you can tell how much of a biologist I am. Why do you care, right? One, I guess if you're a PI, you care because you maybe can get experiments done, in a more reproducible way, right? If you're in a research lab that doesn't include a lot of free undergraduate labor, maybe you also would like to not pay as much, right? You don't want to necessarily hire a whole bunch of postdocs to do kind of these laborious experiments. And also by automating tasks, it naturally can make the experiments more thorough and more exploratory because you are lowering the barrier to these experiments, right? So a common task in the lab is liquid handling, shown as a liquid handling robot here. I actually don't know what kind of liquid handling robot this is, but it looks like many of the others that I'm sure some of you are familiar with. And it basically knows how to do, it knows how to find a well, it knows how to find a pipette tip, it knows how to suck up some liquid, it knows how to move that liquid over to the next chamber and things like that. And these can be programmed, right? And for those of you who have experience with it, right, you go in, you have a spreadsheet, you program in your workflow, and it'll perform your workflow for you, right? And the part that we really want to add on here is the AI agent because embedded in what you do are a lot of decisions. And here we're defining agent just as anything that acts in a decision-making capacity, right? Although you'll see later that there are many different types of agents. Or I would like to define agents here as independent, having the ability to independent act. And so these models have some kind of interactive ability. They have some kind of ability to respond. They have some kind of ability to have some kind of adaptive response, which we might call learning, whether that is learning in the reinforcement learning sense, which is what RL stands for there. And that would mean updating weights or updating some kind of policy for its behavior, right? Some kind of neural network. Or whether it's some kind of large language model like GPT, where you're doing some kind of in-context learning, right? You're providing feedback to the machine, and therefore naturally you're prompting it to give a different answer, right? Kind of like you know, what you saw with RAG, right? Except you're getting feedback directly. So then you want to, you know, be able to perform actions, get some kind of environmental feedback, and then update that cycle over and over again. And that's not too unlike what happens in the lab, right? So consider what happens when you're first learning to do PCR and you don't have, you don't have kappa hi-fi, hot start or whatever it is, which is how I learned to do PCR, and it worked magically right away. But you're sitting there playing with the amount of magnesium and all these concentrations until you get your PCR to work. What you're really doing is you're performing some kind of action, right? You're mixing chemicals together, you're putting them into some program in the thermocycler, and then you're getting some environmental feedback back after you take that, and then you go assay, run it through a gel and assay, did you get the band you expected or not, right? And then based on that feedback, you go back and you loop back around until you have your PCR optimized, usually to enhance the amount of product you would have, for example. And I don't know how CS or biology the audience is, but since it was introduced to biology, sort of like exciting in biology, I thought, why don't we bring that in? And so these are all, this is the central goal of agents, is to be able to perform that for you. And that's not only limited to robotics in the lab, but it's also something that you can use to generate code, right? So code agents are agents that basically write code, just like the code that's used to operate the robot, or carry out any lab instructions, or carry out any robotic arm instructions. And in doing so, you can generate that code and then execute that code and then get feedback back from the system, assuming you have some kind of sensors or some kind of output that you can get back from there, right? And this is typically used uses large language models to do this. And large language models are actually been explored very heavily for this, and there are a lot of specialty language models that can do this very well. So for people who haven't tried to use large language models to generate code, it's definitely worth a try. It's something that it can do very well. I even have one child who refuses to learn to code because he thinks that large language models will make coding, will turn coding into what used to be what math was for a calculator, right? So he thinks it's going away. So there goes my life. Apparently coding is out of fashion now. So how do you, I'm just going to give an example that's not really mine, but belongs to the other people in Arvind's group. And so how do you employ these agents, right? So having a single agent do everything is not really workable. Even in today's large context models, where you can have up to 1 million tokens inside of a prompt, it's just too many tasks to do in one prompt, right? One thought, so to speak, one agent thought. So it makes sense to really break the agents into pieces, and just like you use the lab and have feedback, right? And then get another prompt, right? You get some information, you go back and you change something about the experiment and you do it again. You can have agents talk to each other, right? And so in talking to each other, they can then give each other feedback and prompt themselves. So here are some classes of agents, and I'm going to walk through this in a little bit more detail because I break this up a little bit differently. So these are the different types of agents that you'll code in, right? You'll have agents that involve tools, right? You'll have agents whose job it is to provide feedback, and that's their main job. You have agents whose job it is to rewrite code or to execute code, or basically similar to a tool agent, but a one type of task. And then you have like curriculum agents or planning agents who sort of scope out the overall thing. And these are the types as they're coded now, and And so this is an example, right? So you can have a planning agent over here. It has some kind of memory that's stored, either in a notepad, that goes along from task to task, or in some kind of Python entity write list or whatever. And a common scheme is you have a planning agent. That planning agent creates a list of tasks that need to be done. That list of tasks get turned into a specific list or tree or something by an agent. And that can then be tackled one by one, right? So then you have a loop that basically says, let's have agents tackle this one by one. You have some kind of goal tracking, right? How many did you do? And that can be not necessarily an agent, but that can also be just in code if you have it as a list in memory, or it can be, recorded in memory. You have your overall task prompt, right? Once you've sort of completed all of these the task prompt is the thing that the planning agent is doing. Once it's answered, once it's done decomposed the task and done all of those, you can go back and talk to another agent, which will generate some kind of draft code. This code, depending on your agent, will be correct or not, and likely not unless you're very detailed in what you want. But it'll actually be able to carry out that code. It'll return an error most likely, and then that'll prompt it to it'll code error. It might code again, but then if it runs, it'll try to verify that code, and then if that depending on the feedback from the critic, it'll refine that code, right? Or the critic will say, wait, we need to do something else. We need to use some kind of tool. It'll go to an agent which has access to different tools, like the RAG database you just heard Ozan talk about, right? Maybe it'll retrieve information. It'll return that information to the CodeGen agent, and then it'll cycle around again, right? So this is an example of a workflow, and I just want to break this down for you because I think it's useful to have a view. This is a very fast emerging field, right? So even if you went back to late last year, a lot of the current architecture or frameworks that exist are gone, are completely changed now, right? So within a 6-month time zone, you don't even recognize the field anymore, essentially. So that means every month things are changing pretty much. Rather than we have some examples. There's an example tutorial script that hopefully you guys received with this that includes examples of how to call different frameworks, ranging from LangChain, which will be mentioned in this presentation, which uses, well, we'll talk about it later, to CrewAI, to AutoGen, which is Microsoft, to LangGraph, right, which is the newest one, and probably the most programmer-like. And so those change all the time, but what really you'll retain, hopefully, is some kind of higher level concepts of how this works. So really one way to think about this is as a graph of interactions, which is why LangGraph is maybe the latest one, right? Because I think conceptually people are sort of coming together on this. So it's a graph of interactions where you can think of each node as being an agent or a set of agents applied to a given task. So every node has one task and an agent or a set of agents. And these parts can be reused, right? You can mix up different agents and nodes, but it's the agent node pair that really makes up the node, right? And interaction is something that controls how messages are passed between nodes, right? It can be fixed in that, it can be like a sequential sort of execution where you do task 1, then you always pass the result of that to task 2, right? So like, take for example, like code execution, right? You always execute the code, you generate the code, you execute the code, and you always pass the message to the critic agent, which will then review the code, right? Or verify the code, right? So it will always happen regardless, right? Or it can be a conditional, right? You can generate code, and based upon what that code looks like or what the agent says about that code, you could do one of two things, right? You maybe could just go back to the planning agent and say I'm done, or you could you could execute that code, right? That's just another example. So I'd like to have you guys think about a graph of interactions this way. And so why would you why would you ever recycle agents or tasks? So, agents really are the thing that are given a background, some kind of system prompt with a story. If you actually a fun exercise, if you ask GPT-4 to write a story, a backstory for, different expert agents, right? It'll write their whole life story, right? It'll say, well, so-and-so was born of parents who are infectious disease doctors, and these infectious disease doctors know everything about infectious disease. And, this this person grew up knowing, wanting to know everything about infectious disease, then entered into the CDC where, she made all these policy decisions, and it'll give you a whole paragraph about their backstory in life, and that'll set up the prompt for how the agent behaves. The task is what the job is, right? And the job could be, let's critique or let's read this infectious disease paragraph and see if it represents a threat. It could be, let's read this code, right? In which case this agent might not be very good at it because it's not specified for that. But you can imagine recycling an agent across different tasks, right? Likewise, you can also swap, the same task, different agents, because you'll get different replies. An example of what you might look up, my fun example is always you can Google for the 6-hat thinking system, and basically you ask the same question for all to all 6 hats, and the different hats reply differently, right? One is thinking about safety, one is thinking ambitiously, the other is a skeptic, another is concerned with all the things that could go wrong. Another agent is thinking empathetically, how does this affect the human soul, basically. And it's much better than that, and I am. So that's a little disturbing, but you can sort of mix and match these things. So, but everything boils down to nodes, which are agent tasks, agents plus tasks, and interactions, right? So you can break down everything after that. And so then, if you think about this as a system of interactions, you can break it down kind of differently. You have these nodes, these different agents, and they have different tasks. So for example, you have memory and goal tracking, which can be tracking agents, right? These are useful because you could use a Python list for these too, right? You can track it that way. But sometimes it's useful to have tracking agents because the large language model is giving you some kind of response that has to be parsed semantically, which is to say it's not programmatically, right? You have to actually understand the words and what they mean, and there's some nuance in there. And so these tracking agents, can often be used to just sort of store things in a scratch pad. Is one thing it's called sometimes, where they store pieces of information that'll be carried around through the different prompts. So tracking agents can be used to kind of summarize those and keep track of things. You have interpretive agents, which really, they help glue. My view of interpretive agents is that they help glue things together, right? So they sort of take instructions from other agents and they carry them out. So they're not really there to make decisions. They're really there to carry out and execute those decisions, right? So they're really LLM actions, I would say, right? Because there's also code actions and tool usage, but these are actions that the agent itself are going to take, right? You tell your friend, give me, the top 10 pros of some movie, and they just have to do it, right? There are verification agents, and these are basically error reducing agents. And so as you want to reduce the errors more and more, as your system naturally gets larger, as you scale your system of agents, the verification agents actually become very important. So just like error checking in any system, like a high performance computing system or any kind of code or calculation, the larger that calculation scales to, the more error checking you need to maintain the robustness of that code, right? So these verification agents, as you scale your system, are probably the thing that grows the most. They're the thing that grows exponentially or in a power law. And this is something that you have to be aware of as you're increasing the size of your code. And so, for example, if you're coding something really, really large, you may need agents to verify individual functions or individual steps. And have an agent that actually checks on the critic agent as well, because the initial critic has some error rate, of course, right? And so the way to squash an error rate is to, if a single agent catches 90% of the errors, the way to get to 99% is to have an agent check on the agent afterwards, right? For the most part. And so that's why that grows so much as you scale up. Then there are other parts which are not really agents per se, but they're like tools, databases, specific things that code that can be called. And these are parts that are not I say they're not agents, but they're really still need to be entered into the system in such a way that they can work with the agents, right? So there's a certain format that different frameworks expect. So probably I'll just note AutoGen is probably the most unusual one in that you have to build your own tools for ingestion, within the AutoGen framework. You have to build those explicitly. The other tools generally take the LangChain tools straight off, and there is a way to convert the LangChain tools into AutoGen. But this is just to say that these things are not automatic. You do have to interface in a certain format with the tool agents, and that again changes over time, right? If you see like the React format, then that's kind of the original format, I would say, and just I guess stay up to date. And of course, we can't have a system of interactions without actual interactions. So there are fixed interactions, as I said, which are sequential executions of tasks, right? These are things where there's no real decision to be made. And one way you can see that is, like, for example, so these are just sort of, I'm assuming you do this task decomposition, and then you're gonna, go back and do this goal tracking, and then this is sequential, right? Even though it looks like a loop. The other way you can tell is when there's no real fork in the road, right? Like there's only one arrow going through, that's a fixed interaction, right? Because that's, you go into this node, you have no place to go other than into the next node, right? Conditional interactions are areas where you can make decisions, right? So for example, the critic agent can do multiple things. It could go to a tools agent, or it could refine the code directly and return that back to the CodeGen agent, right? And the critic agent makes its own choice. There's a format, just like there's a format for tool usage. The agents have a format by which they can call out the next thing they want to do if you give them options. And in many cases, you can just let the agent decide on their own. That is a possible interaction, right? You don't give a specification, and you just give the agent options. Another very popular one is that you can actually give specific conditions, and you can give those specific conditions in text, right? You give them in your prompt. You basically say, if you're happy, refine your code. If you're not happy, add a code scale. And you don't even have to define what happy or sad is, but it's sort of better if you do. And so you can do all these things. And likewise with the tool agent, you give them a set of skills, and you have a way of telling them what these different skills are for, right? If you need to look up information, go use the RAG to look up information, right? If you need to go to the web, go to the web. If you need to go to PubMed, because you're looking for something scientific, call the PubMed tool, right? So these all exist, right? Also, you can have retrievers into different databases, right? So you could have a retriever that looks at the code, right? If the code is really long, you might want to look at different parts of it. Or you have retrievers for specific data sources, right? Like other people's codes or things like that. So there's a lot you can do with the tools there. And these are all sort of conditional interactions because you're giving some kind of instructions for, conditional instructions. Think of it as an if-then statement, but it's allowed to be a bit semantic. So it's giving an if-then statement more like giving an if-then statement to a human than giving an if-then statement to a computer. And then lastly, what we started with were decision-making agents, but I wanted to put this last because, you can think about decision-making agents as a single LLM call, right? Because there are a few different variants of this, how you can think about this within a node. And you can make a single call and you can just drive the next step, right? Plan it, and then we're going to go to task decomposition. That's sort of more like chain of thought. That's just sequential, right? But also becoming very common is to have the planning agent actually have a committee, right? So why not have 12 different experts work with you to make a decision? And that can be a complete graph, right? So a complete graph in the sense of like every agent talks on the committee, and that committee globally reaches a conclusion, right? This is, you'll see a lot of automatic interfaces for this in the framework, right? Maybe except for LangGraph, sorry, where you can just put together a bunch of agents and say, hey, go, right? Crew AI calls it a crew, right? You put a crew together, go. You can also have managed discussion where there's a leader LLM that routes things to the agents. That sort of, the leader maybe plans something, then thinks, okay, what kind of questions do I need to ask? Which expert do I need to ask? And then asks that expert and then sort of manages that conversation. Both of those work reasonably well. I don't know that there's an advantage too much one or the other, as long as your framework is stable, right? As long as it sort of completes the task often enough and doesn't get hung up into some kind of circular discussion, both work well. So, one popular tool is LangChain. It has it's one of the older ones. I'd say it's the oldest one that has a large community. But I almost hate to put together slides on these kinds of things because really the community is updating all of the time. So I'm gonna leave the examples in the tutorial, and then you guys can read the pages and figure things out. One thing I'll say with LangChain is it kind of moves in flux in terms of like people adding things and reorganizing, and there are multiple libraries, right? So there's LangChain, LangChain Core, LangChain Community, and just be patient with it. It's sort of like a lot of different things at once. If you find that too disorganized, which I think realistically at this point, it makes sense to do something else other than LangChain because these other frameworks are less bulky and a bit more organized from. The first one in is always the most disorganized probably, and it'll get refactored. But these other areas like AutoGen, these other frameworks like AutoGen or LangGraph are probably also really good. Or if you have or if you fit within the functionality of Crew AI, that also works really well, right? Crew AI, I'd say, has less functionality, but it's very, very easy to use. So those are all things to explore, and I'm happy to answer questions on those. So just to give an example, because sometimes I think people get a little mystified by this thing, and the example could not be simpler because it's literally pass the instruction, do something, just like you would to a human. Like, you say, I want you to load the pipette, or I want you to perform PCR, or I want you to, whatever you would tell a human, usually a, undergraduate, right? Let's say a sophomore in college or something, right? Like that, right? You might tell a postdoc, something like, isolate organoids and grow primary cell lines, and they would probably look up SOPs and figure it out. But if you told that to an average undergraduate, they'd probably be very lost, right? So that just, and one day we may get there with these models, but for now, the intelligence of these models is kind of at that level where if you can imagine talking to an undergraduate who doesn't have that much laboratory experience, you probably would break the instructions down into smaller tasks for them. However, they're still clever. They can still interpret, your non-exact instructions, because you're not saying go to well position 46, at these coordinates, go down the z-axis this much, suck up this much liquid. You're giving them just general instructions still. There's still a lot of interpolation in there. But just, not as much as you might give like a advanced postdoc or something like that. But you literally give those instructions and then you let it go. And then it'll just generate code, and then you'll find out if that code is good or not. And that's it. And oh, there's a movie here for you. So this is Brian doing, he's running the Python script. So I haven't actually seen this, but it's a lot of fun to watch the machine talk to itself. Oh, well, that happens. Okay, let's see how broad. There we go. There's, oh, I see. I see. It's getting an error and then it's going back and it's trying again. So it's writing different code now. So it's getting an error. It's out of tips. It's trying again. And then it's checking on the code and it's saying now, yes, you provided accurately corresponds to protocol directions, right? So you can see this one is very simple because it's just load the pipette. And it figures out in a few iterations, which is pretty good. All right. So I talked about PCR, and so how do you scale towards PCR, right? Because these robots exist somewhere. You can buy them from companies, but that's not the point, right? You don't want to have to learn how to do these yourself, right? You don't want to have to tune, you don't have to optimize, you have to do all this work that normally has to be done in order to do a PCR experiment. You would like to be able to treat the robot like, a reasonably advanced student and say, figure this out yourself, go optimize this, and then, make a figure in my paper for me. And you have, if you break it down, for those of you who know PCR, you might think maybe it's not that complicated, but it is actually, many, many steps at once, right? You have to mix some kind of master mix, right? You have to get some kind of basically chemical parameters together in your mix. And that has many dimensions, if you want to think about it that way, right? Because it's sort of like how much calcium, how much magnesium, how much of the polymerase, and so on. And you also have thermocycling, what's the temperature, what's the time of that temperature, how many cycles, how cool or how warm those cycles are, and so on and so forth, right? And so you actually have many, 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 many decisions to make. And if you were just to explore those exhaustively, it actually is a terrible idea, right? We could try counting it out, but it's really not, it's not practical, right? Because these things actually take money and they take material and they take time, and material can often be finite. And so what humans do is they sort of, based on experience, have some kind of you know knowledge of kind of where to search. And that's, and the large language model in this case is really helping you search that space and coordinating all the instruments and tasks together. And so this is really, how, this is the challenge of scaling. And then this is how, this is just the interface, right? So this is how they manage to coordinate these different instruments. So there's just this issue of scaling here. That's also getting these things to talk to each other. That's more of a technical issue. And why do we think this will work? Well, we think this will work because we know that at this point already that we can scale these agents themselves, so it's not much of an exploration as the time these slides were originally made, but you sort of you sort of expect this works because you know that if you can get control of these experiments and feedback, the large language model can learn and return things back and is good at producing JSON code, and not producing too many errors, right? So basically this works in terms of scalability because you have some control over the errors. Let's see, there are videos here, which is great because we can just watch them, maybe. Okay, so this is a little smallish, but this is, seen this setup before. There's the arm, it goes, it's going to figure out what to do. Going to pick up a plate, it looks like. Going to think about what to do with this plate. Right, it's coded up this other robot. Do the next task. We have our action cameraman over here. All right. It's loaded into the robot. So now it's loaded into a robot. Now the robot has to figure out what it wants to do. And it has picked up a pipette tip, small pipette tip. It is decided to grab from this well. It is gone and placed something into this other well. So it can learn to perform these aspects of the experiment. And so if it can learn these, you can imagine, making the output more downstream, right, than PCR, and continuing this further and really scaling full automation beyond sort of an individual assay, so to speak, right? And so with that, I am done. And thank you all very much. And credit goes to these guys for putting together these slides. I'm happy to take any questions, assuming I can get out of this screen.
Great, Nick. This is very impressive. Is there a code walkthrough for this section or?
There is. Let's see. I thought maybe Priyanka
Oh,
deposited.
okay. Yeah. Let me.
We were debating whether it was really worth.
No, I mean, code is always good. Maybe
I'm happy to go through it if
I
it's
don't
helpful.
see Priyanka here.
Oh
Maybe
no,
you
no,
can walk through it.
it is her birthday. She has the day off. So
Oh,
let's
okay. Yeah.
hold on. I'll just open up the code if that's
Open up the code, and then we'll start with some. Maybe we'll open up for
questions
some
on the
Q.
code.
Yeah, questions first, and then we can do a code walkthrough.
Sure. So people can ask questions while I'm finding my code here. Let's see. I have it somewhere.
So kind of a quick one. While that experiment was kind of running, there seemed like there was some like decent pauses between the steps. Is it like actively thinking about what to do next in those pauses, or is that just like that's just how fast those robots move, or what?
So good question. And the answer is I don't know, but I'm willing to take a guess with you. And so I've seen these robots in action before. I've used them in the lab. They typically very slow to move. So I would be surprised if there was anything else happening other than them just moving along slowly. So let's see. I wonder what the latest version of this. Does that answer your question?
Yes, thank you.
Okay, perfect. So let me just I just want to pull down well, we'll work with whatever version we have and then I'll see it as we go. So let me pull this up here. Let me find my Zoom window. Let me share screen again. Let's see. Where's my there? Okay. All right. So can you guys see this screen? So I have a few
Yep.
versions.
Yeah.
And we'll see if this one is an interesting one. So so this tutorial was designed in mind. We've given this we presented agents a few times, and one of the bottlenecks we hit is when everybody tries to hit either collab or hit a model or hit some kind of resource all at the same time. And so this one is meant to be very small and maybe run on your laptop if your laptop is, sort of, beyond a certain spec, right? So it's not totally unreasonable. So the first thing we do in this tutorial is we actually load up a local model. So you'll see that we install, here are our installs. One of our installs are Ollama. You also could install LM Studio, but basically the goal here is to run a model locally, right? So we import Ollama, we pull the Llama 3 model, which is the 8 billion parameter model. And if we do this, then now we have this model running locally on our laptops. And this is something you can do reasonably well, right? If you have, I think, 16 gigabytes of memory in your RAM, you can do this, right? Assuming you don't have other programs taking up a whole lot. If you have less than that, you could consider running the 5.3 or 5.2 models. Those are smaller, right? Around 3 billion parameters or so, or 2 billion parameters. and you know, they have some functionality. Now, of course, the higher level model you go to, the less erroneous your responses are. But for the so you can replace these calls with other models, but you know, for now, this is really just meant with that in mind. And yeah, so this is just an example of calling. You know, Olama, it's really that simple. You just have to follow this format, this syntax, and you say, why is the sky blue? And it returns things in a certain syntax, and different models return things in slightly different syntaxes. So this one, you have to look at the message and the content, and that can differ depending on, you know, if you're using, you know, it changes sometimes, just you might have to look for your results in a different place. And there, your 8 billion parameter model tells you why the sky is blue, right? And then you can ask, why is the sky green? And this one is a little bit more of a, you know, so this is also a client, right? So I should say this is just a straight up response. And then when you're using agents, very often you're going to rely on a client. In this case, the client is on the local host, which is your machine. But you can replace this with a call to another inference server somewhere, right? And again, you know, so now instead of the main difference here is that instead of the Olama chat, you know, you're gonna go to the client for your chat, right? So this is still going to Olama because I'm serving it on my machine, but now it's going through an API interface, right? So now I can ask, why is the sky green? And this one, you know, it tells you the sky is not green, which, you know, for those of you who know, when you see a green sky, green tinted sky, that usually means a tornado is potentially coming, right? So that's a warning sign for you. If you ever go outside and, oh geez. So my references get aged, and my students I talk to tell me this all the time, but if you ever go outside and you think it looks like the Matrix out there, you know, then you should be a little careful. So there, and then you know, you can start asking it questions. And so we gave a couple of examples. Here's just a random math question that one of my students came up with, and I'm not going to go over it. It has to do with eigenvalues and whatever, and you guys can think about it. But basically, you can ask the machine this question, and the point is that that Olama gets it wrong, right? So the right answer is E, but it says A. And so we put this here to show you what the advantages of having agents, right? So, you know, so there are some things that individual, you know, LLMs just individually called cannot solve that agents can, right? You know, and if you've learned about chain of thought and things like that, you can do that too. And you can just think of an agent set up as setting up its own chain of thought or its own tree of thought kind of for you, right? Because you can have these conditional, you know, or sequential links. So the first interface I'm going to introduce you to is Crew AI. Crew AI kind of has this nice concept. It says, well, there's the agent, there's the task, and there's the crew, which is the team, and then there are these processes. And basically, you know, I initialize my model, my LLM, you know, in using the OpenAI sort of interface, right? So most models follow the OpenAI format. It's not that they are OpenAI, but most people use the OpenAI format. And then here, you know, we say, okay, let's make several agents. There's the expert. There's an alternative expert. You know, there's a peer reviewer. There's a verifier. And now we're going to have them all talk to each other. And we're going to say, hey, here's the different tasks. So this particular way it was written was each agent has a specific task. So then you have the agent task nodes, and then you basically put together a crew. And the crew are these agents that you just specified, and these are the tasks. And you'll notice inside of each task, they specify what agents are available. And so you can make that multiple agents if you want, but in this case, it's just one for simplicity. And then this is a hierarchical process, right? So a hierarchical process means that there's an LLM manager walking through these tasks, right? Figuring out the right order and so on. If you made them sequential, it would just walk through these tasks one after the other. And so then it carries out a whole conversation with itself, which is kind of like what Brian's movie was. And it kind of, you know, the cell is cut off because it just goes on for a long time. but you can see like the format. This is the React format where there's a thought, there's there's action, so there's a certain format that things get returned in that allow the conversation to keep going, and it's called the React format. And I forget what it stands for, but basically it's made up of these entities, right? And then and if you were to scroll down here, you would see some errors basically where it breaks out of it because the model has to return things in a certain format to work, and the 8B model doesn't always perform super well, but so there are some errors you'll get sometimes.
Nick,
to
this
a larger
quick question here. And we've also seen these kinds of similar issues for other kinds of computational workflow tasks, and Llama 3 seems to struggle. Have you guys tried any systematic experiments between various open source and or open weights and closed models?
No, I have anecdotal stories for you, but I wouldn't say we did anything systematic.
For these same things, if you tried like one of the GPT-4 models, would that generally be fine?
Yeah, they work very well. So the GPT-4 models are functionally trained, right? And so they're trained
Yep.
specifically for agents. And so OpenAI trains all of its models functionally, and GPT-4 is the one that you can scale the best because of the lowest error rate. Mistral 3 also has specific functional training, and I haven't tried it yet, but it's I think initially it looks like it's behaves better because of the functional training. And I think more and more open source models are coming with specific functional alignments. So that if that makes sense, right? So they're coming.
Yeah, that makes sense. So you at this stage, right? Would you basically recommend that if you were thinking about using these kinds of things in these kind of automated lab experiment type flows where the error is obviously loss of material and like loss of equipment time and so on, right? At this stage, probably this is where state of the art is, that one would have to use one of GPT like models.
Yeah. I would say so, unless your task is very small, right? Yeah, I mean, basically, right? For any reasonable size task, you would need GPT-4. Right now, that seems like the best. I've played a little bit with Claude 3, but I haven't played with the latest one. The latest one is actually a pretty big jump
Yeah,
up.
the 3.5 seems to be pretty good, right?
Yeah, I haven't played with that in the agent setting, but that seems like a big jump up. And on the code generation, it's really good. So I wouldn't be surprised if that also worked really well. I'd say if there's a lightweight model that works better than you would expect, it's probably the Phi models. They're not like super smart, and they're not, and Microsoft outright says they're not super smart. But Microsoft's goal with those models is basically like, can I make a small model that would one day fit on your phone and could help with some basic tasks, right? Not like big things. So it's not meant to scale a lot, but it seems to be meant with production in mind. So that I think for the 3 billion parameters, I'm not going to say it's great, but considering how small it is, it seems better than it should be, right? Because 8 billion works, but it kind of like barely works. And then the fact that you can get a smaller model, usually around that size, they really, below that they all fail. But that's the one that will do some stuff at that lower size. Yeah, and then the Mistral family seems to be more geared towards functional training. Yeah, hopefully that answers the questions. And Llama 3 is a step up from Llama 2.
Yeah, thanks.
So it is improved. Yeah, and if you, well, it's a different topic to say, but you can carry out the functional alignment yourself if you get really into it and need to use a smaller model. But I think for the most part, you would rather use GPT-4 because you don't have to worry about the scale of compute. You just have to worry about some kind of dollars that you're giving to them. And so it's faster and you don't have to worry about that. You get the right answers more often and doesn't cost a lot more. Is that helpful?
Yeah, that's great. Yeah, keep going.
All right. So then, so that's Crew AI. And Crew AI is kind of easy. You just sort of pull the crew together and you're like, let's discuss this. Or we have a set of tasks to get done. Let's do that. Then there's AutoGen. And so maybe it's actually not surprising that 5 class of models work reasonably well, because of course, Microsoft has its own agent-based framework. So, there's probably some reasoning there. So you can pull like the 5.3 model and, it'll work well. We did, you could try swapping it out in this example. And this one has been changing a lot actually over the last few months, and has gained a lot of functionality, and is, professionally maintained, which is nice. Has, some disadvantages over the open community and but some advantages as well. You can configure different models. You can, this is just configuring and figuring out what models you want. You can get different ones, and then you can choose which ones you want, and then you can do the same thing, right? And these agents are now have different possibilities, and the equivalent to what you had in Crew is going to be these conversable agents, and you're going to give them some kind of description, right? And then notice what you have in AutoGen here is you have the allowed transitions specifically specified, right? So in Crew AI, you sort of specified, hey, let's do this sequentially, or let's let the LLM manage how I want to do these tasks. In AutoGen, you're seeing the graph concept come more front and center, right? So basically, the student here can pass messages to the expert can pass messages to the alternative expert can either pass it back to the expert or to the peer reviewer can go to the expert, the verifier can go back to the student, right? So these are the only things that are allowed, right? And so it's not, it's not purely sequential, and it's not purely an LLM just deciding what to do. You can make these specifications. You also can specify, I don't think there's an example of it here, but you can also specify conditional transitions as well. So you can specify how and when those transitions occur. And so it gives you more control over the granularity of how you want the conversation to be generated, right? Or say that, for example, you're worried about materials and cost, and you would like to do a simulation first before you actually launch it on the robot, because you don't want to waste PCR master mix. You don't want to have it do things 100 times before it figures out how to do something. So you could sort of condition it to say, hey, until the simulation actually passes, our check, we're not going to actually go to the next, robot or whatever. So here's how, you can have a group chat manage. You have a group chat, right? And then you have the transitions are specified by the allowed transitions. You can still have a group chat manager, and then you can basically initiate that conversation, right? And then now it carries it out, and it goes on to the next step, and the next step, and the next step. So this basically, as opposed to putting the whole crew together and going, kind of puts in the first node and lets the rest of their graph go, right? And so you can see here that it's you're starting to expose more of the code, and with that comes ease of control, and also more options, right? But you also but the code is still, if you're using it in the modes that AutoGen is sort of built in, it's still not very hard, right? It's still kind of like Crew AI in that sense. And AutoGen in general has a lot of customizability, but if you go sort of off the beaten track, you have to read the documentation carefully to find those things. Interestingly, LangGraph, so I've had some summer students this summer, and I sort of let them test all of these things and kind of as my own personal experiment, wanted to see what they gravitated towards. They've both gravitated towards LangGraph, which is interesting because LangGraph, as you'll see, is going to be the most verbose, right? It's going to be the most exposed, most verbose, most control, but it's also sort of like, in some ways, the most laborious, right? But you guys will get to make your own decision. And so, so let's see. So did we get
Nick, that was a very interesting comment. Can you share some more thoughts there? I think Karthik has been not sure if
this one is
he's
not.
around, but he's been quite keen on LangGraph. So
Yeah.
maybe some more commentary on that insight of why they gravitated towards LangGraph. I think that would be very interesting.
Yeah, and I realize this one is not the latest version. It doesn't have LangGraph in there, but we'll see if I can find the other one. So yeah, it's just so comment wise, let's see. So so I think personally, my rationale for this, why people are getting attached to LangGraph, is because in AutoGen, there's like the easy way to do things, but then when you have to go off-road, it's like a different syntax or whatever. And LangGraph tends to follow the same kind of, it feels like the same syntax, right? You sort of can guess what's next in the scheme. So it's sort of more like it's more like a scripting language than AutoGen, which is a bunch of function calls, and then some functions are great, and some functions you have to just know the magic formula. So my takeaway from this is that my students would prefer to be autocomplete engines than to read the documentation, which is fair, because that's kind of how I code too. So I don't know if that's like the information you're looking for. But if I give an example of LangGraph, if I can find it, then you'll see what I mean. It's just more, the calls are just longer and more, oh, here. So, okay, this is a bit messy. Maybe it's not perfectly the latest one, but there's some code in here. So you can see like, here's the agent state. You're now creating agents and you're specifying, and those agents can carry out states, right? So LangGraph makes exposed like a very state space, sort of a state space model as well. So agents can actually do different things in different circumstances. Like if you complete a task, the agent will do something different now, right? Or behave differently now. And so you explicitly can specify the agent, you explicitly specify the node. You can you then create the agents, and then any and then the node essentially, and then you have to put together the graph, right? So you're so in some sense, I was very surprised that this is the one they liked, right? Because you can see it's more complicated, right? Because you're actually defining the router, how messages get routed, you're defining them in a graph. You're adding nodes to the graph, you're adding conditional edges, you're adding, edges as you want, whatever edges, right? And you're manually, unlike if you remember AutoGen, it just had allowed transitions, right? And it was sort of like easy to manage, at least in the example. But now you see this example actually grows quite a lot and is very verbose. And yet they like it, right? So it's verbose, but it's kind of repetitive, right? And then you compile the graph and then you launch the graph, right? So that's this sort of like I wouldn't be surprised if like advanced users like LangGraph a lot, but it seems like even the students, and these are undergraduate students, I think, in their sophomore year, right? Seem to prefer LangGraph. So, you can take that into account as you sort of move forward with your work. And so it just gives you a lot of control, and it exposes everything, which, has some advantages. And AutoGen also involves some work, like when you're incorporating tools and things like that. So there's So, there's no sort of free lunch unless you are doing exactly what the easy functions in AutoGen or Crew AI are meant for. But in LangGraph, there really are no such set paths, right? You just sort of make your graph, compile, and launch. Is that useful to the conversation?
Yeah, I think so. I think this is great, and it'd be great. Next week we're gonna run through a number of actually one of the hackathons is on agents. We were thinking about computational science agents, but I think we might be able to bring in some of the agents, integrating to automated labs as well into that. And I think there's a bunch of these things that'll be very exciting to sort of push forward in the hackathon in the next couple of weeks.
Yeah, so the main thing that about agents, so you can do it in an autonomous lab. I think the main advantage with or when you're first playing around with agents, the only thing is speed is nice. So when you're working with the lab system, the lab system is kind of like a slow computer, right? Because it has to do something.
Yeah, it's the response time is not at the same response time as as code execution, right? But I think that actually also brings in new issues, right? That
Mhm.
about the fact that the error rate actually makes a lot more
No impact. Yeah.
impact, right, on productivity and actual. So I think these issues, right, will be very, very interesting. I mean, we can run it. I mean, we can do sort of synthetic experiments, right, with as in you can mimic that. Oh, it did the measurement and then this is the answer, right? But those are all things that will sort of help us understand how can we reliably operate these things. And also the lab setting has another problem, which is that the lab code, right, is much of course specialized, right, depending on sort of what kind of autonomous lab experiments are you using, and like the kinds of code that's there in LabVIEW and other kinds of lab embedded control software, right, is much more limited, right? So that might even boost up the error rate, right, even more, versus like computational computational agents, right, where there's a lot more code available, and of course you can do like execution and like things that you're talking about here, right, to like verify if things are running fine, whereas there's not as much access to experimental autonomous agents or autonomous experimentation.
Yeah. No, so I'll say that I do so a lot of the work I play with is separate from is separate from typical use cases, right? And so what happens when you're not in a typical use case, because talking about niche areas of science is kind of like speaking in a different language, right? And so since those are not as trained, the models don't perform well when they're as well, and they have more errors when you're talking about very specific scientific concepts, right? Or special scripting languages or things like that. So you have to employ the usual tricks in terms of prompt engineering, but also I tend to use a lot of verification agents, like a lot. So for example, I know Ozan was presenting RAG, right? If I'm gathering information, I might not just do RAG, right? I might do RAG. I might grab the top 100 relevant texts according to the vector database, and then I might feed them all, one by one to an agent to ask, is this text relevant to the information I wanted to look up? And it may say yes or no. And out of those 100, for example, if I'm really in some specialized area, maybe 3 will be relevant, and I'll say, well, now I have 3 bits of relevant information. I'll use those 3, right? So that's basically an error checking mechanism, right? And then you can imagine that, you have those 3, you can also send another verification after that to say, okay, look at these 3, and does it really, answer the question from these viewpoints? Or once you get the answer, does this make sense, right? Can you look over the whole thing again and make sure that the whole loop made sense? Just kind of like if you were like a supervisor, you would do that too, right? So in terms of squashing the error rate, I would say it's sort of like a power law game. In terms of power law with regard to the number of agent calls versus the error rate. So you have to just keep increasing the number of checks and then nested checks, and then that'll squash it. And if the compute is much cheaper than the experiment, then I would lean very heavily on building a robust verification process. I don't know how to describe it exactly. So I used to work at Mayo Clinic, which is very like legal, committee
Yeah.
bureaucratic, SOPs everywhere, committee has to approve, another committee has to approve. So I view it almost as like, I have the job of setting up a Mayo, SOP
Yeah.
for, some patient sample, right? And even though like, this will involve like 10 different committees and 15 different processes, at the end of the day, it's sort of slow, but it's like, it can be less error prone, right? So it's kind of like that, if that makes sense by analogy.
Yeah, that's great. Yeah. Thanks. Yeah, keep going.
Yeah. And that's it actually. So I'm just here for questions at this point, and we're close to time. So
Yeah, perfect. Is there anything more left in this book, or?
this person was so this particular student was playing with Gemini.
Yeah,
I'll
maybe a little bit, right, on this Gemini, if
Oh,
we s-
it's just a different model, right? So Gemini is, so one thing good about this is now you can see what the API call is like, I guess, right? So you have to put in your API key, you have to put in your username, you have to have an account. You have to pay for this, right? Because having an API account with Gemini or any service, you'll have to enter your credit card information in, or your advisor's credit card information if you can steal it. Whatever, somebody's credit card information. And then you'll have to you do the same thing basically, but just with the difference that so in this particular case, this is all that's required to call it, right? If you just put this in and you have these environmental variables set, it'll just go. In other instances, you may have to change that call for like other models, but basically you have to call that model and enter that information in. And then, and don't leave it in your code and post it on GitHub. That's not a good idea, by the way. Don't hard code that in, just because I've seen a lot of people do that, and that's a good way to get your account stolen. So then you do the same things, and now you can just have the Gemini model do it, right? And the Gemini model performs not as well as GPT-4 and Claude, but it does decently. So it's just an example of something different.
Perfect. Yeah, thanks.
Yeah, so this gets into an argument with itself over here, and that argument goes on forever. And it was having some errors using the tool, so it's having some functional issues training, right? Yeah, but that's part of the gig. Some things work better than others. Gemini is not as much in the same ecosystem as OpenAI. Oh, and there. That's not good. Don't do that. Do not do that, because now you can go into your account and you can reset your API key anytime. So I will tell the student like, hey, you may now want to change your API key. So this will be bad in a little bit. If you touch in the next 2 seconds and know his username, you might be in trouble. But yeah, that's sort of it.
All right, fantastic. Okay, I think we're almost at time, so maybe 1 or 2 questions. Anything else in the chat? I don't see anything. All right. Thanks, Nick. This was fantastic. And I think it's a very exciting frontier. And yeah, thanks to you, and then also to Priyanka and I guess Brian, who
Yeah.
helped with the slides as well.
Yeah.
Okay, great. Thanks. And then we'll come back at 1:30 p.m. for integrating with external tooling and fine tuning and various other aspects. So see you all in the afternoon.
Thank you all. See you.
Thanks. Bye.